Okay, so we'll move forward with another problem from our textbook, Fundamentals of Fluid Mechanics, 4th edition. Authors are Mansun-Young and Okishi. It's problem number 11.47. Upstream of a throat of an isentropic converging diverging nozzle at section 1 here, velocity is 150 meters per second, pressure is 100 kilopascals, absolute pressure, and T1 in centigrade is 20. If the discharge flow at this point is supersonic and the throat area, this area of the throat, is 0.1 meters squares, determine the mass flow rate in kilograms per second for air. You're given gamma 1.4 and the gas constant is 286.9 Newton meters per kilogram Kelvin. So we're given the velocity, we're given the pressure, we're given the temperature at state 1, we're also given the area at the throat. Now in any problems involving converging diverging nozzle, I must know the state of my flow. I must have information of its compressibility. That is through the Mach number. Is it supersonic, is it subsonic, or is it sonic? At state 1 it's given, so I need to find it at state 2 is given, I need to find it at state 1. For me to find it at state 1, so I need Mach number at state 1 is velocity at state 1, which is given, over the speed of sound. So that is V1 over R T1K, or gamma. That's equal to 150 over 286.9. T1 always in Kelvin, 293. Gamma is 1.4. So the Mach number is 0.4372, approximately 0.44. This is very important information. This applies when my Mach number is smaller than 1. I have subsonic flow. So at state 1, my flow is subsonic. Now in a converging diverging nozzle, when I'm going from subsonic to supersonic flow, the only way that is achieved is at the smallest area, which is area at the throat, the flow should be sonic, also known as the critical state, or we say that the flow is choked. So to find the mass flow rate, I am given the area at the throat, I need the density at the throat, and I also need the velocity at the throat. Now since it must be sonic, that is to say Mach number must equal to 1 at the throat, therefore I'm dealing with the critical state problem. So my density and my velocity are critical state velocities. What does this mean? It means I must use critical state relations or formulas. Now, my goal is to find the mass flow rate. I'm given the area, so I must find the density and I must find the velocity. Knowing that at the throat Mach number equals to 1, this implies my velocity critical at the throat equals to the speed of sound, which equals gamma R T critical. Therefore, for me to find V critical, I must find T critical. I am given T1 and I must find T critical. I have no direct relation with the formulas I'm given to move from T1 to T critical, but I am given these two relations in the formula sheet. One is relating the stagnation temperature with T critical. Next, I'm giving the stagnation temperature with any temperature anywhere in the state, in our case is number 1, equals 1 plus gamma minus 1 over 2 Mach number squared. So for me to have move from T1 to T critical, I must go through the T naught. Therefore, I use number 2, and I can say T naught equals T1 1 plus gamma minus 1 over 2 Mach number squared. That is 293. 1 plus 1.4 minus 1 over 2 Mach number 0.44 squared. So that gives me an approximate answer of 305 Kelvin. So I have T naught, I can easily find T. So from relation number 2, gamma plus 1 over 2, so I have 305 over T critical equals 1.4 plus 1 over 2. I can get T critical equals 253 Kelvin. Now I can plug this back into my equation and I can find V critical is gamma R T critical, which equals gamma is 1.4, R is given 286.9, T critical always in Kelvin is 253 or 253, so V critical is 319 meters per second. Therefore okay, now I have found V critical. The only thing for me to find is the critical density. So again, my goal is mass flow rate and V naught. So I have this, and I need to find density. For me to find density, there's two ways. You can choose either or to get to the same answer. Density critical from the state equation equals pressure critical over R, that's a constant, T critical. I have my T, I have R, I need to find P. P naught can be found from P1. Again, same principle. I must relate P naught in both equations, P1. These equations are given. So for me to get from P1 to P critical, I must find P naught, which is common in both. So this is the first way. The second way, once I find P critical from here, I can plug it in the equation. And I find my critical density. This is one way. Second way is to use the relations of the density. You need critical density. Okay? For me to find critical density, I need stagnation density, which I don't have, or I need the density at state 1, which I don't have. But density at state 1 is P at state 1 over R T at state 1. Once I find this, I can use the same principle and I can say, well, this is also a given formula. I can find my stagnation density, everything else is given, and finding this I can plug it into the second formula that relates the stagnation to critical, and I can find my critical density. You can use any way, and you'll definitely get to the same answer. Okay, so I'm going to use one of them, and I'll move forward. So I'm going to use the second one. So from the second one, I have the state equation I have P equals gamma, so rho RT. This implies rho is P1 over RT1. P1 is 100 kilopascals, so that's 100 times 10 to the 3 Newton per meter squared. I have 286.9 given, and T1 is 293, so I have density at 1.1896 kilogram per meter cube. Perfect. Now I've used this. I'll use the second line here to find the stagnation density equals rho 1 plus gamma minus 1 over 2 Mach number squared 1 over gamma minus 1, that is 1.1896, 1 plus 0.2, gamma is 1.4 minus 1 is 0.4 divided by 2, so it's 0.2, 0.44 squared, 1 over 0.4, that is 1.3081. Now I will use the third relation here to find the critical density. .3081 over critical, this is kilogram per meter cube. Gamma plus 1, that's 2.4 over 2 into 1 over 0.4. I get critical density 0.8295 kilogram per meter cube. Now I have everything I need to find the mass flow rate. Therefore, mass flow rate is density times area at the throat times the critical velocity. So I have 0.83 approximately times the area is 0.1, and V critical is 319. So my mass flow rate is 26.5 kilograms per second. Okay, so this is the problem. You need to pay attention those few small things relating T at your state to T critical must go to T stagnation. Same thing applies for pressure. Relating P1 at state 1 to P critical must go through the stagnation value. And also, it's very important for you to assess what is the flow state before and after, and then you can say the flow at the throat is sonic. This will help you use that the velocity at the throat equals to the speed of sound, and then you can use this relation. So this is the types of problem that involves the critical state.